Now that we've learned the definitions of continuity and discontinuity, we want to discuss some specific examples where the graphs are not pre-drawn for us and we'll have to figure things out analytically and possibly graphically. So we're going to discuss the continuity of each function, each of these functions, and I'm going to put a little note up here and say both analytically and graphically. That way we can see them both. Now, technically I could do numerically as well, but numeric is just a table of values and it's kind of boring. All right, so let's start over here with letter A. So I have a function f of x, which is equal to 1 over x squared minus 9. And I know from experience that that is x minus 3, x plus 3, because I learned how to factor in algebra class. Yay, algebra. Okay, so let's think about this. This particular function I've known about since algebra. I know that it has two vertical asymptotes. So namely, if the denominator is equal to 0, then I know I'm in trouble. That denominator would be x minus 3, x plus 3, which would mean x minus 3 equals 0, or x plus 3 equals 0, which means x equals 3, or x equals negative 3. These two equations are actually the equations of vertical asymptotes. So these two right here are vertical asymptotes. We learned that in algebra, right? Values that do not divide away from a simplified rational expression and from the denominator are vertical asymptote values. All right, now think about what that means. Vertical asymptotes means that the function f of x is discontinuous at x equals plus or minus 3, right? It has two discontinuities at each one of those, and they're non-removable, right? Because there's no limit. The way vertical asymptotes work is that there's no limit and there's no function value. They actually kind of break every aspect of continuity, right? So not only does f of 3 not exist, right? F of 3 not only doesn't exist, but it also doesn't have a limit either. All right, so now let's verify that I am indeed correct with a graph, which of course I have drawn in Desmos. And here it is. So if you want to see it, there you go. Right, so 1 over x squared minus 9, this is what it looks like. And you can see you have vertical asymptotes here at negative 3 and a vertical asymptote at positive 3. All right, so graphically, I'm seeing exactly the same thing, namely that I don't have a function values. So I would just draw that at negative 3 and 3. So x equals 3, x equals negative 3. I have asymptotes, and my function looks like this. I'll give myself a little scale here. So let's say like negative 7 to 7, and I don't remember, negative 5 to 5, something like that. And there you go. So graphically, we can see we have the same issue. We have vertical asymptotes at those two values. So vertical asymptotes. And you can see it graphically. Now, technically, they asked us to discuss the continuity of the function, and we've only discussed the discontinuity of the function. I mean, they go hand in hand because they're kind of like opposite sides of the same coin. But since we were asked to discuss the continuity, we can say that this function is continuous at all values except for these two. So what we want to say is all real numbers except for these two. So we can say from negative infinity up to negative 3 joined with negative 3 to 3. That's a union symbol. Union with 3 to infinity. In other words, all real numbers except negative 3, or plus or minus 3. How about that? There we go. So that's another way you can write it. Of course, we're in calculus, so we're very used to, hopefully at this point, interval notation. And that's the way we'll write it. All right, on to letter B. So letter B seems like it's going to be the same in some respects because it's a rational expression, just like letter A was. I'm actually going to change it just for the sake of it. I'm going to call this one g of x just to keep them straight, and this one h of x. That way, keeps things nice. Okay, so for g of x, I'm just going to notice real quick, this numerator is going to be able to be factored just like the denominator was in the first problem, which is this. Now, I'm not going to divide away quite yet. I know that discontinuities happen whenever the denominator is equal to 0. I mean, that's a big no-no. So that would mean x plus 3 is equal to 0, which means x equals negative 3. So I'm going to have some kind of discontinuity at x equals negative 3. But it's not going to be a vertical asymptote. And that's because for this particular problem, x plus 3 and x plus 3 divides away and leaves x minus 3 left over. Now, those are not equal expressions. Those are equivalent expressions. So the graph of this g of x is going to graph a lot like that line, x minus 3. However, it's going to have a hole in it at negative 3. So my function of g of x will be discontinuous at x equals negative 3. Now, what kind of discontinuity is it? Well, you'll find out soon enough when you do the graph, but I'm right in that it's a hole. It's a puncture in the graph, like a hole in the graph. So therefore, it's a removable discontinuity. All right, now let's see if I'm correct. So if I go back to my Desmos graph, I turn off part A and I turn on part B. Part B looks like it's going to be a lovely, lovely line. However, at negative 3, let me drag my mouse along. So at negative 3, whoop, did you see it right there? Let me show you. Right here. Look at what it does. So there's a hole in the graph. You wouldn't necessarily know it originally when you graph it. However, if you play around with it a little bit, you'll realize that there's a puncture right there. Oh, okay. So that means that my graph is a line, but it has a hole in it. There, I fiddled around with the graph a little bit just to make it a little more permanent. So I'm going to copy this graph onto my paper, and then making sure that I put in the nice puncture, the nice hole right there at negative 3, negative 6. Now keep in mind this graph is not the original, or excuse me, is the original graph. It's not x minus 3. If I graph x minus 3, let me do it in like red so you can see it. X minus 3 is a line, so they're equivalent everywhere except for at that one puncture. And that's because that denominator divided away. So those two expressions are very similar, but they're not exactly the same. Okay, so let me go back to my paper and then push it up right here. And so we can see that we have a removable discontinuity at x equals negative 3. Now, if we want to discuss the continuity of the graph, we would say that the function, g of x, sorry. I forgot that I wanted to change the name. So g of x is continuous everywhere except for that one spot that would have made the denominator 0. So from negative infinity all the way up to negative 3, joined with negative 3 to infinity, right? So everywhere except for that one hole. All right, last but not least, let's look at h of x. Now, h of x is something called a piecewise function that you should have seen in pre-calculus. Piecewise because it's in two pieces, multiple pieces. All right, so keep in mind that these are both polynomials. So if you look at x plus 1, that's a line, right? We know what x plus 1 looks like. No, not going to have any discontinuities. And if we look at x squared plus 3, also a polynomial. So since they're both polynomials, both pieces, if you will, let me make a note. Right. Since both pieces of this particular function, there we go, of this function are polynomials, we only need to check x equals 1 because any other value would be fine, right? 0, or excuse me, 2, 3, 4, 5, 2.5, 2.25, it doesn't matter. They'll all be fine, right? This is a smooth line, that's a smooth curve, that's a parabola, that's a line. So we only need to check x equals 1. Need to check x equals 1, right? Because that's the break point between these two graphs, or between these two pieces of this graph. Okay, so how are we going to check that analytically? So we don't have a fraction like we did in these other two. So these other two we checked analytically using stuff we learned from algebra class. But how are we going to do it now for this particular function? And the answer is, well, we're going to test the value of 1 in each of these and see if they're equal to each other. Because if they are, that means that the two sections are gathering together and joining up. But if they're not the same, then that's a sign that this is discontinuous at that value. So let me check. Let me just call these functions something just for the sake of it. I'll call this a of x and b of x. Terrible names, right? So let me check a of 1. So a of 1 would be 1 plus 1, which is 2. B of 1, right, part B, would be 1 squared plus 3, which is 1 plus 3, which is 4. They're not the same. Since they're not equal to each other, that means that there is a discontinuity. H of x is discontinuous. Continuous. Oops, I lost my extra u in there. Discontinuous at x equals 1. What kind of discontinuity is it? Well, it's going to be a jump discontinuity because you're going to two different spots. You actually just prove that the limits are not the same. So you would say it's a jump, which is, by the way, non-removable. Non-removable discontinuity. Now, you might not know it just looking at it. I mean, I know it is because I've just proved that the limits are not the same. So, but if you want to see it visually, you can look at the graph of it, which I just happen to have, right? So it's a jump non-removable discontinuity. And then if I turn this off and turn this off and go here to see, let me kind of zoom it up for you to see. And there you have it. So it's a parabola on the left side and it's a line on the right side, and this parabola is going to 4 because we just proved that, and then the function is going, the line is going to 2. Those are not the same values, right? 2 is not equal to 4. Therefore, this is a jump discontinuity. The limit does not exist. All right, so I'm going to draw that graph really quickly. All right, so there we have a quick sketch of this graph, and we can see I was correct in that we have that jump discontinuity. So now we would say that this function is continuous. H of x is continuous basically everywhere except at 1. So continuous from negative infinity up to 1 joined with 1 to infinity. Now, on a side note, if you wanted to discuss the discontinuities that you're seeing, we could add that in just for fun. So this particular one over here on the left, it's vertical asymptotes. Vertical asymptotes violate all 3 aspects of continuity. There's no value at those values, at those x values. So there's no function there, there's no limits there, and therefore they're not equal to. So if you wanted to know this violates all, so f of x, I'll just add a little note down here. F of x violates all 3 parts of the continuity checklist. Right? That's the way vertical asymptotes are. Vertical asymptotes automatically break all 3 parts of it. Right? There's no function, there's no value. Now number 2, or letter B, g of x has a limit, but it has no function value. So g of x violates condition 2, or condition 1. Violates condition 1. There's no function value. But not number 2, because even though there's no function value, there is a limit value. So the limit as x approaches that -3 exists, but the f of -3 itself does not exist. So f of -3 does not exist, is what I'm saying. Over here, we have a function value, right? So there is a function value at 1. So h of x violates condition 2. There's no limit. Violates condition 2, but not condition 1. Because there's no limit, but there is a function value, and it's right there. It's that closed dot. So f of 1 exists, but the limit as x goes to 1 of, oh, sorry, h of x. Sorry, I forgot that I made this h. I keep doing that. This was g as well. Sorry about that. All right, so this is g of -3, and this was h of 1. Right, so h of 1 exists, but the limit as x goes to 1 of h of x does not.